Good morning, children. I hope you have referred our previous topic in chemistry, what we have done, right? It was on our periodic classifications of elements. So we have went through the history of the classification of our elements, right? So now, where did we ended up till our who was it? It was Mendeleev's periodic table with his law. That was our last topic which we had discussed about. Now let's get into the new topic. That's next with the invention of a new periodic table. That's our modern periodic table, as you can see on the board, right? Modern periodic table, which is actually invented or discovered by a scientist named as Moseley. Okay, it's Henry Moseley. So let's start our today's class. Now let's see who invented this modern periodic table. But before that, what did we conclude in the last class? We ended up with the periodic table invented by, who was it? It was none other than our Mendeleev, right? So Mendeleev was, I told you, his periodic table is modified and is the same thing is carried on to our modern periodic table as well. There, what was his demerit? I didn't tell you the demerits, but they took his demerits as into the consideration and then they modified the periodic table. The arrangements, the idea what he had, everything were considered, but only thing was the property, the basic, what was his, the Mendeleev's periodic law. It stated that, or our periodic table law, right? Periodic law, what do you say? States that the properties of elements were the periodic functions of its atomic masses, right? So here there's a slight change. The same definition goes on. I'll let us go to it later. First, who invented this modern periodic table? It was a scientist called as Moseley. His full name was Henry Moseley. Okay. He was the one who invented this modern periodic table, and this is the same periodic table that we are using till date. There was no other modifications made to this particular table. So let's start on and look into the detail what are the basic features of this periodic table. Okay, there were some demerits in our Mendeleev's periodic table. It was nothing else but they could see that new elements which were discovered couldn't fit again. There was a small issues to group them into these his periodic table. What was his periodic table? How many groups and how many rows, periods did we have? We had 8 groups. Those are vertical columns, right? And 6 periods. But then the elements which were found later on couldn't be fixed or couldn't be placed in that particular order. There was some small mistakes where the scientist faced a few small problems that the properties were differing somewhere. Okay, so they analyzed again and they found that out. What was it? I'll first tell you the definition. So this person called Henry Moseley stated a law called our modern periodic law, and I'll tell you the statement. You better note it down properly, because as I told before, you should not change your definitions and the laws. Okay, they should be same sentences as in this textbook. So our modern periodic law states that the properties of elements are the periodic functions of its atomic number. So you could see that there's a small change. Could you identify Or didn't you identify what was a small change? It's the same statement, right? There's a small change. What is it? I'll just write it here. In our Mendeleev's periodic law, I'll just write the short form. We used atomic mass, right? But here in Henry Moseley's, we are using, in our modern period, we are using nothing else but atomic number. Okay. So what is atomic number? I'll tell you in detail later. First, let me tell you or describe what is the difference with the old periodic table which we had by Mendeleev and the modern periodic table. Here we had how many rows I told you? That is, we had 6 periods and 8 groups, right? But here we have how many? We have 7 periods and 18 groups. So did you see the difference? There's a very wide range of difference, right? That's why. So what does this indicate mainly? As time passed on, new elements were found, and they couldn't be placed right within that restricted column, though he was quite intelligent and clever, and he had given the places for the future elements which would have been or which should have got discovered. Still they couldn't place them properly, so there were more than that, and so this person, that is our Henry Moseley, ended up placing or making a table, a much bigger table with 7 periods. Those are, what are they? Horizontal rows, right? And 18 groups. Those are vertical columns. So this is the main difference. Okay, and what are the main first difference is that in the definition, what's the law? The older law was by Mendeleev was, it states that, what periodic law states that the properties of elements are the periodic functions of its atomic mass. So before getting into the details of a modern periodic table, there are many properties that you have in your textbooks. Okay, there are trends and all, but before that there's no basics for it or definition for it given in your textbook, but you should know that. Okay, so that's why I'll give you some basic definitions for that properties before that. Okay, so you better note it down somewhere because it's very important. Unless you know what is it, there's no use of learning the trends in modern periodic table. So please note it down. I again repeat, it's not there in your textbook, but you have that for your studies. Okay, yeah, let's start. First, starting with our atomic number. What is atomic number? Is it the number of atoms? No, it's not. Then what else it is? Atomic number is the number of electrons present in an atom. It may be any atom. I think you have heard of electrons, and you also know that electrons are negatively charged, right? So we have a particular number of electrons for every individual atoms and elements. Okay, there are certain different numbers allotted for each elements, and that's why they have ended up becoming that particular element. So let's see what are atomic number. Let me give you an example for our atomic number. Okay, I'll take a element which you know carbon, right? So let's start with carbon. How do we indicate carbon? We indicate it as C. You can see that if you open, just now you can open your periodic table in your textbook. You can see 2 numbers. One mentioned above, that is here, it's 6, and below you can see something like this. Okay, there will be two numbers indicating basically. So we have the atomic number on top. Okay, atomic number, as I've told you, the atomic number is always written on the top, that is our 6 for this one atom of carbon. Now, and some number you can see right below, this number indicates our atomic mass number. Okay, this is called as our atomic mass number. This is atomic number, or you can also say it as atomic mass, it's fine. Now, what is atomic number? I have told you before, it's nothing but the number of electrons or protons present in one atom of that particular element. Okay, so here it's carbon, so the atomic number is 6. So what does it say? The number of electrons or protons. It's not electrons and protons, okay, it's electrons or protons. So you can just say electrons, it's fine. So the number of electrons present in one atom of carbon is 6. So that is nothing but our atomic number of carbon. Okay, now what is this? 12. Atomic mass number. Atomic mass number is nothing but the number indicating the total number of protons, neutrons present within the nucleus of this carbon atom. Okay, yeah. So this is atomic number, this is atomic mass. This is actually not much importance as of now for you. So this is important, our atomic number. So you should look more, you should concentrate more onto this. Okay, so this I have to just give you an example. I have taken this. Okay, so we just don't need 12, so I'll just remove this. Now let us represent the structural form of this carbon atom. So first we have the nucleus of the carbon, and then I'm putting 2 circles around our nucleus. So these are the regions which are indicated where the electrons can be found. Okay, the electrons are actually not located in a particular place, it keeps on rotating. Okay, it's not located at a particular place. It's like our planet and the solar system, no? You can see that sun and it's keeping on rotating, the other planets are rotating. Similarly is our nucleus and the electrons around it. Okay, so these are called our shells. So we represent in a form a circle. So these are the places where electrons are found. Now let's start. So how do you, every element, there's a different number of shells in each element. Okay, it varies with each element. So for carbon, now it's 6, right? So I'll show you. I think you have a brief knowledge, you should have a brief knowledge about all these things, but still if you have forgotten, let me just give you just to remember. These are shells, right? And each shell has its own name. So first we'll start from K, okay, and then L, it goes on like that. So shell, we have it as starting from K, L, M, N, and it goes on like that depending on the size of the atom and the increase in the atomic number. Okay, so for carbon it's 6, atomic number is 6, right? I'll show you how to locate the electrons first. Okay, so you should represent, there's a particular way of representing the number of electrons around that particular nucleus. Okay, so in K, that is our first shell, you can place only 2 electrons. Then it goes to 8, then again 8, then after that it's 18, and it goes on like that. Okay, so what you can do is just, I think you may not require more than this probably. So we'll just maximum you need to know is up to 3 shells is sufficient, I hope. So let's start. So as I've told you before, it's 2. So first you have 6, right? Number of total number of electrons present in this particular atom, that is one atom of carbon, is 6. So our atomic number of carbon is 6. How do I indicate it? I'm indicating this is our nucleus. So around the nucleus, right? I'm indicating 2 electrons first, right? I told you in K shell it's 2. So 2 I have indicated here, and remaining how much? 6 minus 2 is 4. So remaining 4 atoms, electrons, I'll place it here. And always you should remember that electrons won't be like together like this. Why did I draw it like this? You can just draw it, I should have drawn it like this only, right? No, it's wrong. It should always face oppositely, because as I've told you before, electrons are negatively charged, right? You can know, you see that. So this particular, they face repulsive force towards each other. So there's the maximum stable configuration or the stable arrangement is perpendicular, the maximum distance that they have occupied, right? This is the stable position for them. So always you look into that. You draw it perpendicularly. Yeah. Now you have placed all the 6. So what is this is the shell L, right? So what is it? The number is 8. So what does that say? These are the stable numbers, like stable number of electrons that have to be placed in them. Okay, so that we say that as configuration. The arrangement we say at configuration. So this L shell should have been 8 electrons, but we have only 4. So is the carbon atom stable? No. You can see that our L shell should have has the capacity to accommodate 8 electrons, but there are only 4 electrons here. So what does it do? This is not stable. Okay. There's something called stability that matters in each and every atom, including us, right? You have 2 legs, you can't stand in one leg. How long will you stand? You'll somehow keep your second leg, right? So there should be some stability there. Similarly is our atoms also. They have a particular stable configurations where they actually try to attain that configuration. So our stability is 8 for L shell. We here have only 4. So our carbon is having the tendency to search for 4 more electrons to make them stable. So there's some new property coming up that is called as our valency. Okay, what is it? I'll write it here. It's nothing but valency. Okay. So we have a new property called as valency. It's a state of any atom to share, that is the number of actual valency. The definition for valency is the number of electrons that are given or obtained, that is used to react with other element. Okay, the number of electrons that are used to react with other elements. That is, let me give you a detailed explanation. So the number of electrons, as I told you, used to lose. So I have told you, right, there are 4 electrons. So what is the option for carbon to become stable? Either it should lose these 4 electrons. That means it should donate these electrons to some other atom, maybe any atom that requires similarly, or gain 4 more electrons, right? So that it becomes 8. So that number, whatever the number which is lost or gained, or it can also share with some other atom. So shared, anything, then that number is indicated as valency, and these electrons present in the outermost shell is called the valence electrons. Okay. So here, how many number of valence electrons are there? It's 4, but valency depends. When you consider carbon, there's a special character for carbon. What is it? It has 4, right? You can see it's half of 8, so it's half stable. So it's called the tetravalent, okay, atom, carbon. So because it has tetra means 4, right? 4 atoms, right? 4 valence electrons. So therefore it's tetravalent, and its valency is always 4. Okay, only for carbon it has a special. Let me take another example of hydrogen. Hydrogen, we have atomic number as 1. Okay, so this is a nucleus, and now we just need the first shell, and you place that first, what is it, first electron, that is 1 electron, right? You have so you are placing it here. So what is the first, for the first shell, how many electrons should be there? It should have 2 electrons to become stable. So it just has 1. So what does it do? It can't give. If it gives, what happens? This element is no more existing, right? So it should attain one more electron, or it should gain one more electron. So it binds with another atom, it may be any atom, and it gains one more atom to attain the stable state. So what is the valency of the hydrogen? It's 1. How many number of valence electrons are there? It's again 1 only. I'll give you one more example to clarify. Like here it's 4 and your valency is 4. You have 1 and your valency is 1. So take another example, that is for chlorine. The atomic number is 17. Okay. So for 17 is our atomic number. So I am allotting it like, let me draw the structure. This is our nucleus. This is our K shell, and we are placing 2 electrons. I'll indicate it in different color, only the electrons, okay, because you may not find, yeah. And then we have our L shell. So how many L can contain? 8, right? So I'm drawing 8 electrons. 1. Here it can, the electrons can, since it is 8, right, it's stable, so here the electrons can get paired up. So how can it be? It can like pair of electrons, okay, 1 2 1 2 2 and 2. So it's stable, right? Again the repulsive force doesn't matter, so it's having a stable state there. Now let's see how it's 2 plus 8, how much it is? 10. So we have 7 more to locate. So let's put them. This is our M shell, and we have 7 electrons. So 1 2 3 4 5 6 7. You can see it lacks 1 electron, right? It should have had 8 electrons, but it has only 7 electrons in the outermost shell. So what should we do? What is the choice for chlorine now? Is it to give away all these 7 electrons, or it's easier for it to just take 1 more electron, right? That's better than losing the entire 7 electrons. The easier job is to attain 1 more electron from something else, right? So here I'll show you the difference between the valency and valence number. So the number of valence electrons of chlorine is, what is it? The number of valence electron in chlorine, it is nothing but how many? The outermost, the number of electrons present in the outermost shell, right? So it is 2, 4, 6 and 7. So valence number is 7. And what is the valency? As I've told you, valency is the electron that is used to react with other element, or to that involves in making it stabilize. So it's 1 electron, right, which it has to get at, which is coming in, right? It is attaining 1 more electron to make it stable. So what is our valency? Our valency is 1. Okay, so you may have got the difference, right? It may be the number of electrons that's getting in. So that's 1. Here it's 4 and the valency is also 4. Here the valence electron is 1, the number of valence electron is 1. It needs 1 more atom, so it is taking 1 more atom, and therefore the valence. Here you can see that there are 4 electrons, that is the outermost electrons present in the shell, the outermost shell. So there are 4 outermost electrons, and therefore the valence number is 4. And valency, it needs 4 more electrons, so the valency is also 4. Here in hydrogen, you can see that we had 1 electron in the outermost shell. It needs 1 more electron, right? So the valency is also 1, and the valence electron is also 1. Here we have the number of valence electrons are 7, that is the number of electrons present in the outermost shell, right? And the valency is 1 because the number of electron that is coming in, right? It needs one more electron and the valency is 1. Okay. So our next property is electronegativity. We have completed with our valency and our atomic number. Now going to electronegativity. As I told you, it's not electron negativity, it is electronegativity. It's a property. So what is it? Note the definition. Electronegativity is the tendency of an atom to share or to attract a pair of electrons, okay, to itself. So what is it? It's the tendency of an atom to attract a pair of or an electron towards itself. So that is electron. Why is it attracting actually? Always know that to become stable. Okay, yeah. Now let's go into the detail. I'll show you what is electronegativity present in the structure. Let's take chlorine. Taking chlorine, as I've told you, what is our valency? Valency is 1, right? That means, which means it needs one more electron to get into a stable state, right? So electronegativity is, what did I say? The number of electrons or the tendency to attract a number or a shared pair of electrons or electron basically to attain a stable state, right? The next property is our atomic radii. You know what is radii, right? You would have studied in your maths. You're studying also, I think. So let's start with atomic radii now, or atomic radius. I'll tell you what it is in detail here. You have seen this, right? This atom, again, this is our atom. So here the atomic radii, again note down the definition. The atomic radii is the distance between or distance from the nucleus center, the nucleus to the outermost shell of that atom. The distance between the nucleus to the outermost shell of that atom. Okay. So for chlorine, it's from this nucleus, the center, to the outermost shell. So I'll show you this from this point to this, right? From the nucleus to the outermost shell. This distance is our, what is it? This is our atomic radius of chlorine. Okay. This varies from element to element based on the size and the number of shells, which goes on increasing. Okay. So this is our next. That was our fourth property, atomic radii. Next, now let's get into the new property, that's our metallic character. So for each element, it may be a metal or non-metal or metalloid. There are three types, right? Metal, non-metal, metalloids. You may have heard, or we'll learn it in detail, okay, further. So first, let's see what's our character, the property now. It's our metallic character. Okay. What is it? Basically metals, with the elements which any element that acts as a metal has a particular property. What is it? It is nothing but it has a more tendency to lose electrons. Basically, as I've showed you before, let's take chlorine here. Is chlorine a metal? What do you think? It certainly is not a metal. Okay, why? It's a non-metal. Because what is the tendency of chlorine? Is it to lose electron? No, it needs one more electron. So the tendency or the property of chlorine is to gain an electron, right? To attract one more electron. So is it a metal? No, it's a non-metal. So basically, what are metals? Metals are the ones which like to donate or give the number of any number of electrons from its outermost shell. Okay, so those are called metals. What are non-metals are the ones which actually gain the electrons, like our chlorine. And metalloids are semi stated, like they are in between metals and non-metals. They sometimes do give, and sometimes they also accept the electrons. It depends on their stability with reacting with other metals. Okay, so this is metallic character. It's simple, right? Yeah. So these are the main properties that are mentioned in your textbook. Only the names are given and the definitions are not there. So I hope you have noted all the definitions in detail whatever I've told you. Okay, let's get into the trends or the properties of our modern periodic table now. So children, let's go to the trends, see what are the properties and trends of the modern periodic table, the table as such. Okay, so please open your periodic table, your page number 30. You can see such a table. Okay, yeah, so here as you can see it's starting from hydrogen, and these are groups, right? Vertical column, it's ending, it's going till thorium. So you may not know the names, it's fine. As you can see, this is down the group, and this left to right is across the period, what we define. Okay, top to bottom, that is downwards we say down to down the group, and from left to right we say across a period. Okay, yeah, now let's see how the trend goes. Even you can look at the back of your textbook, right? You can see there's a beautiful periodic table there. It's more clear. So you can see, right, this is down the group, and this from left to right I will tell from now onwards as across the period, down the group and across the period. Okay, so these are the two terms that I will be using from now. So let's see the trend. So first property. So first properties are atomic number, right? What we have learned. So atomic number, as you just look into your textbook also, right? Whenever I ask you to, even you can plot this table on your notebook. Okay, because it's very important. The entire chapter from now is completely dependent on this particular table. Okay, so you have to know these are important. So first property, as I've told you, is our atomic number, right? Atomic number. So what does it go like? Across the period. Across the period in the sense from left to your right of your table, right? Sorry, from left to right. You can see that. Let me start from the first row. It's from hydrogen, it's 1, and as you go, this first row has only 2 elements. That's your last has helium has 2. So and again down you can see the second period has 3, 4, 5, 6, 7. It goes on increasing, right? So across the period, what you can see, the trend of atomic number is goes on increasing. This arrow mark is for increasing. Okay, you can also write increasing, but for increasing. Okay, this represents increasing. Just note. Okay, so it's increasing across the period. Then down the group, what is it happening? Even atomic number down the group also it's increasing only, right? So even down the group it's increasing. Okay, so it's increasing as I've told you. I'm not writing it as increasing, you have to note it down. Okay, yeah. Next property. What is our next property? Next property. So second properties are atomic radius. Okay, so let's see how is the trend. So here what you have to focus on or note down is atomic radius across the period actually decreases. Okay, it decreases. As I have told you, down arrow I have represented for decreasing. Okay, yeah. So atomic radius decreases across the period and increases down the group. I'll tell you why. Okay, just note down this point in your in your notebook. What are you writing this down? So why is like across the period you have to look into it. Like you have to note that you have same number of shells present in the one particular period. Suppose it's your first period. As you can see, the first period has, I told you, 2 elements, right? For that you see that hydrogen has 1 electron, helium has 2 electrons. So these both are fitting in first, that is our K shell, right? So it has only one shell. So across the first period we have one shell. So it goes on across second period, entire row has two shells. 3 has 3 shells, 4 shells, and it goes on like that. Okay. So since we have same number of shell across the period, what's happening is the electrons keeps on increasing, right? As the atomic number increases, the electrons keeps on adding for each and every element that goes like in the row further, right? So what happens? The nucleus tends to attract the outermost electron, every electron towards itself. Okay, so what does it do? It attracts all the electrons, and therefore the effective nuclear charge, something called effective nuclear charge, is present. That is the nucleus with respect to the outermost shell, that attractive force, okay, that is your effective nuclear charge is more. As you go on from left to right, the effective nuclear charge increases, because more the number of electrons in the shell, it has to spend more energy, right, to attract all the electrons. So what happens is, when it pulls more, it gives more energy to pull the outermost shell, it shrinks. The size gets shrink, right? When you, so similarly, it has to produce a bigger amount of energy to actually control all the nucleus, all the electrons that is present in the outermost shell. So what happens? Resultingly, the atomic radii decreases. Okay, so what is the reason? What you give is atomic radius decreases across a period, like left to right. Since effective nuclear charge is more, that is enough. Okay, what you have to write the point. Next, down the group it increases. How is it? Because down the group what's happening is, as you see in each period, right, first period had one shell, second period has two shells, third period has three shells, right? So as down the group, the number of shells keeps on increasing, so the size automatically increases, right? So what happens? Atomic radius down the group increases. Okay, yeah, and of each element it depends. Okay, it may be increasing or decreasing. It depends on how it is bonded to the other element. So it doesn't have any particular trend, so let's leave it aside. Okay, it depends. Now fourth property. So but valency, what is it dependent on? It's dependent on the number of valence electrons present. Okay, yeah. Next, let's go to a fourth property, is our metallic character. Okay, metallic character. Now metallic character, as I told you, what is a metal? Metal, the element which tends to lose electron is basically the metal, right? That means which has lesser valency, right? So how does it go across a period? It decreases across the period. Okay, it's basically losing the electrons. Okay, so metals are the ones which tend to lose electrons. So the best elements which actually like to lose are the first ones here. Why? Because as you can see the atomic numbers over there in the periodic table, as you go down the group, see the first I am going looking into the group 1. You can look in your periodic table. In the group 1, what you can see is the atomic number increases, like you have odd numbers, right? 1, 3, 11, 19, 37, and all this, when you put them into with respect to this our K, L, M and no, you have that stable configurations. When you put into each shells, what happens is you will have one single electron in the outermost shell in the first group. Okay, so what will you do? Is it easier for them to gain extra 7 electrons to make it 8 and become stable, or to is it easier for them to lose electron? It's easier for them to lose that one single electron what's there in the outermost shell, right? So what they do, so the first group, okay, the first group and the second group probably are more metallic than the others, because as you go across the period, metallic character decreases across a period, and it remains constant, or sometimes it may also increase group, because it depends on the reactivity. It may lose very fast, sometimes it's very easy for them to lose. Some elements may have require more energy to lose the outermost electron, so it depends. So it may increase or it may remain constant down the group. And then is our non-metallic character. Okay, non-metallic character. So as you can see, metallic character increases. So what is non-metals? Non-metals are which actually gain, right? Non-metals are the elements which actually tend to gain the electrons. Okay, so what happens? Non-metallic character across a period, it increases across a period. It's just opposite. For your easiness, just remember that it's just opposite. Okay, so non-metallic character across a period increases, down the group it decreases. Okay, and sometimes again it's the similar case, because the number of electrons are same. So what happens? It may remain constant as well. Okay, yeah, so this is the trend. Now let me show you in detail about, just look into this periodic table in behind your textbook. You can see that there are pink boxes, right? So till there the metallic character exists. That means these are all belonging to metal categories. Okay, but the metallic character goes on decreasing. Still these are the metals. Now the pink boxes, you can see on top they have already mentioned in detail. It shows these are metalloids. They show both metallic and non-metallic character depending on the bonding with other elements. Okay, and the next after pink, the yellow part, you can see, no, those are strong non-metals. They are all non-metals. So as you can see, what can you see here? From here these are metallic, so the metallic character is going on decreasing, right? Here metalloids. Then after that what happens? It's non-metal, so there starts a non-metallic character. So the non-metallic character goes on increasing across a period. So that means the tendency to gain electrons are increasing across the period, and the lose electron is decreasing across a period, right? Yeah, so that is this non-metallic character. Now fifth last property is our electronegativity. Electronegativity, I am writing in a short form. Electronegativity, I have explained you what is electronegativity, right? The tendency to attract pair of electrons or electrons towards itself. Okay, yeah, so what happens? After looking into this, you can actually say how it depends, right? It is almost similar to our metallic character. Okay, why? What is it? To attract, right? Tendency to attract the electrons. That means that is similar to a metallic character, right? So what happens? Similar trend it follows. Electronegativity decreases across a period and remains same or increases down the group. Okay, so these are the 6 properties that are mentioned in your textbook, and it's very important to know these trends. Now you can see, for you may get confused, right? So you just remember these two are having similar trends. Which all have the similar trends? You can see that our atomic radius, right? Our atomic radius, our metallic character, and our, what is it? Our electronegativity. These 3 have similar trends, right? And the others are having the opposite trends. So you can just, for your like to become more easier for you to study, just study that these 3 are having the similar trend. That is, remember the trend, remember any one trend so that you can understand, and the others are in opposite. Okay, but this is a exception. Don't forget, atomic number increases both ways. Yeah, so this is there ends your entire chapter. And one more point you have to calculate, they may ask you to calculate the number of electrons present in particular period. They may give you a period number, okay, or the number of shell. that is your N. Okay, you have a formula in your textbook, you can just look into it. It is 2n square. Okay, this is the formula what you have here. What is N? N is the number of period, or the it may be the number of shells. Okay, so it's both the same. You can see again in your periodic table, the first period they have written it as 1 on the left side. First period you can see that the shell, how many atomic number we have? 1, here we have 2, so the electrons can be grouped or placed in one shell, right? Just in one shell we have 2, that is your K shell. So what does it indicate? It's period 1 and the number of shell is 1, so both are same. So what they are asking is N is our number of shell or period. Okay, yeah. Now why is this formula used? This formula is used to calculate the number of electrons present in that particular period. Okay, they may ask you, calculate the number of electrons present in period 1. So what do? You just substitute 2 in place of N. What do you say? They have asked you period 1. So number of shell is 1. So what will you put? 1 square. So you have 2 and the number of electrons present is 2. Similarly, you are going to next one. Second. So the period number there is 2, that is number of shells is 2, and so you put 2 square, so it becomes 8. So the number of electrons that can be accommodated in the outermost shell is 8. Not only outermost shell, the number of electrons totally in that particular period. Okay, yeah. So it goes on like that. You can just look into your periodic table and you can analyze it later on. So let's end the class, wind up the class here. So this is all about your periodic classification of periodic classification of elements. This is actually just an introduction to your periodic table. You may have all the other chemical reactions related chapters based on this particular periodic table. So it's very, very important. If you fail to understand this, this is the basic for your entire chemical reactions that you study further. So this is the basics. You should know this. Okay. And more chapters in your chemistry text, your textbook, that is one is your metals and non-metals, and others are acids and bases. Okay, so for that also this is the basic knowledge what you have to know. You don't again we can't repeat it at that time, so you should keep remembering it. It's very important. Now this is the thing which we are applying. The entire chapter is those chapters are based on this particular chapter. This is applicable there also, so it's very important. Please do go through it. There's nothing much. Keep it in a brief and do remember. Okay, so yeah, let's wind up the class. I hope you have understood everything. Just revise, go through it again and again, and do remember the trends. These are very important. I repeat, please write it down somewhere, stick it on your wall or somewhere so that you see every day, you don't get messed up. You can write, as I told you, you can first categorize things into one section, like which all have the similar trends, you can write it in order, and which have different opposite trends you can write next, and finally you can write the exception, like our atomic number. No, it has both increasing, so exceptions you can write it at the last, or however you feel, but you should remember this. Okay, keep this, mark it as very important. Anyways, so take care, revise it, re-revise it, do study. Okay, bye.